Hello and welcome to today's ICRP workshop. My name is Nina Petuzzi-Hens, and together with David Sutton, we are the chairs of the task group which has developed organ and effective dose coefficients for common radiographic examinations. This group has prepared a report, which, like other previous ICRP reports, is available for public consultation prior to the final publication. And I will share my screen so that you can see my slides. So the objective of today's webinar is to give you a flavor of the report and to seek your views. Today we will be addressing the main points of the report through presentations by task group members, and we will be happy to receive your comments and thoughts by the 16th of August, and also answer questions during the dedicated session of this workshop. This is today's agenda. I will give a short introduction to the work of the whole task group, just to set the framework of the work, and then a short introduction to the consultation document. Donald Miller will continue and discuss the projections considered and the definition of the fields. Then Yeon Soo will give a brief introduction on the ICRP reference computational phantoms and on the methods of calculation. And then David Sutton will demonstrate some application of the dose coefficients and the electronic supplement and viewer. These presentations will last about an hour, and then we will have 20 to 30 minutes at the end dedicated to your questions. To the QA session, which I will moderate, I will come back later. Since we are going to talk about dose coefficient, let me first remind you what is a dose coefficient. Exposure of a person can be quantified in terms of absorbed dose to certain radiosensitive organs of the human body. As these quantities cannot be measured in vivo, it is common practice to use simulations for their determination. In this report, the dose coefficient relates a calculated dose quantity, either the organ absorbed or effective dose, to a measured quantity, such as air kerma or kerma area product. The dose can be then estimated by multiplying the dose coefficient with one of these measurable quantities. Now a couple of words about before introducing the document, I would like to say a couple of words about the task group. For many years, the ICRP has produced reference dose coefficients for common diagnostic nuclear medical procedures. The ICRP has established our task group to provide reference dose coefficients for radiographic, CT, and fluoroscopic X-ray imaging procedures, which they haven't been addressed before by the task group, by the ICRP as a whole. The task group is mandated to perform Monte Carlo radiation transport simulations in a series of reference imaging examinations and to report the resulting organ absorbed and effective dose coefficients. The scope of this work includes the use of the reference voxel computational phantoms of the ICRP, which correspond to the reference ages of the ICRP system, male and female, newborn, 1, 5, 10-year, 15-year-old, and adult. Also, the recently developed ICRP pregnant female phantom series is employed. Why we're doing this work? The field is not new. but there is no gold standard and no agreed set of phantoms. Therefore, those coefficients developed with different methodology are not directly comparable and could result to confusing disagreement of estimated doses. The new dose coefficients developed with a widely accepted ICRP method would standardize the procedure of converting dose metrics across modalities, such as CAP for radiography and fluoroscopy, and CDDI-VOL and DLP for CT, to estimates of effective dose or some surrogate of effective dose. There are 5 work streams of the work of this task group. The first 4 ones that you see in this table are covering the reference patient. FGI covers both the reference and non-reference adult patient. And by non-reference, we mean patients who have different size to those represented by the current reference phantoms. At a later stage, the work of radiography and CT will be extended to consider non-reference patients in order to examine the variability. But the workshop today is dedicated to radiography for adult and pediatric patients of reference ages and size, and also for optimal radiographic procedures of exposure. To compute their reference dose coefficients, we need reference phantoms, which are models of organs and tissues and their composition, image-based models of the skeleton, definition of the radiation source and field, and radiation transport codes. Now, a couple of words about the document. But first of all, I would like to introduce at least the name of the authors and the developers of this work. This is a group of international experts, and I would like to express my appreciation for their work. Short summary of the method. For each procedure to be simulated, the following have been identified. Anatomical landmarks on the phantom. They have been determined by the 2 radiologists of our group, and also the beam characteristics. Monte Carlo calculations have been carried out for monoenergetic photons in 1 kV steps. The results can then be convolved with any X-ray spectral distribution that the user wishes to choose. For convolution purposes, the dose coefficients are reported as organ-absorbed and effective doses of fluids at 1 meter distance from the source. We also provide a large number of branch dialog spectra, and these are reported as organ-absorbed doses per cap, per air camera-free in air, and per fluence also at 1 meter distance from the source. The dose coefficients of this work were calculated with the current ICRP dosimetric methodology. That means the use of the ICRP 103 recommendations, including the values of the tissue weighting factors, use of the ICRP reference voxel male and female phantoms, improved skeletal dosimetry, definition of age-dependent effective doses based on male and female phantoms. And I should emphasize that the effective dose for this report is calculated per ICRP 103, the current recommendation. So it's calculated for adults and children using 1 single set of tissue weighting factors, which relate to age, sex, and population average risk coefficients. This is the list of the comments. The list of the contents, which they cover most of the topics that I have mentioned. And also, there is a chapter on application of dose coefficients, with David will come back to this later, and uncertainties and limitations, and also an annexes giving more details in some specific subjects. The data files are the most important part of the report, and provide organ-absorbed dose coefficients for both male and female phantoms separately. The report also provides for each examination a value of the tissue-weighted equivalent coefficient for either male or female, depending on whether the examination is performed on the male or female phantom. The effective dose coefficient for an examination can be obtained by taking the average of the two, and this is also given. The publication is aimed at all those who have an interest in patient dosimetry and optimization, including national and international authorities, medical physicists, radiologists, radiographers, researchers, and other radiological practitioners. For example, we believe that our data will be very useful to organizations such as ICRP or similar national organizations, which are collecting data on medical exposures to assess the medical component of radiation exposure to populations. And I would like to close now my introduction by a summary. The organ-absorbed and effective dose coefficients provided at this report are estimated for the reference person at each reference age. They are specific to the exposure conditions. They have been calculated using the ICRP methodology. The calculated organ and effective dose is the dose which the reference person would experience and is not directly applicable to the individual patient. For proper interpretation of the effective dose, we are referring to the respective paragraphs of the report, as well as to the ICRP report number 147 on use of dose quantities in radiological protection. So I'm closing now, and thank you very much for listening. I will stop sharing and ask Donald Miller to carry on.
Thank you, Nina. As soon as you stop sharing, I will start.
I stopped sharing.
Very good, thank you. And I need to find, here we go. We'll use this one. Can you see my screen?
Yes.
Very good, thank you. So this part of the discussion is a discussion of how we chose the radiographic examinations to be studied and determined the correct projections for each one and determined how each one would irradiate the phantoms. So these are our aims: to select radiographic examinations for modeling, and then to define the field coordinates for each examination to be used as inputs for the dose calculations. Because we're using ICRP phantoms, we needed to translate the field for each examination to the appropriate location on each phantom. So the first thing we needed to do was to select the examinations. And the goal was to select both adult and pediatric examinations. And the intent was based primarily to reflect those that are most commonly performed. While extremity and dental radiography are extremely common, they were not considered because they are both relatively low contributors to effective dose. So instead, we chose adult radiographic exams based on their relative frequency in the UK, in Europe, the US, and in unscare healthcare level 1 countries. And this table shows you the frequency of various examinations per 1,000 adult populations, with the most common one at the top, which is the chest, far and away the most common radiographic exam outside of dental radiography around the world. And then pelvis, abdomen, lumbar spine, cervical spine, and thoracic spine in decreasing order. The frequencies vary slightly from UK to Europe to the US, but they're roughly this order. And for each one, we modeled specific projections. That is the way that the X-ray transverses the patient to impact the image receptor. And if you're not familiar with this, PA is posterior anterior, which means that the X-ray beam goes from the posterior aspect of the patient to the anterior aspect of the patient. Anteroposterior AP is the opposite, and so on. So we specified specific projections for each of these examinations. And then we turned to pediatric radiography, and the approach was similar, but not identical. We included examinations that were performed reasonably often on infants and adolescents, but also those that are perhaps less commonly performed, but that result in either high exposures or exposures to more radiosensitive organs, specifically examinations of the skull and full spine radiographs for scoliosis. We don't have the same level of data for frequencies for pediatric examinations that we do for adults, but we do have European guidelines, and we do have a paper from the US that give you relative frequencies for some of these examinations. And again, the examinations are relatively similar in terms of frequency: chest, pelvis, abdomen, lumbar spine, and then thoracolumbar spine just for neonates and infants. And we added scoliosis and skull, as I mentioned. And again, we chose the appropriate projections to model. The abbreviations are the same here. We then needed to determine how each of these examinations would irradiate the phantom. So we modeled each projection based on typical or optimized field sizes and positioning, and then the anatomy we expected to be visualized based on a number of factors. First, on a standard textbook of radiography, which includes illustrations of appropriate radiographs that are essentially ideal, and was intended to show student radiographers what the radiograph should depict. We also had radiographs from a UK hospital, because the textbook is a US textbook. This gave us European practice as well. And then Dr. Applegate and I, both of our radiologists with more than 20 years of experience, we looked at the textbook, we looked at the UK radiographs, and then we adjusted the projections on the phantom based on our experience and both of these other inputs. So initially what we did was we looked at the outline from the textbook and the clinical input from the radiograph, and the modeler gave us a projection defined as what was irradiated in the midplane of the phantom. We looked at that and determined if it was acceptable or not. If not, we gave specific instructions about how to modify the appearance. The projection was revised. We looked at it again. Sometimes this iteration went through 3 or 4 versions. Eventually, we decided the projection was acceptable, and then it was submitted for simulation. And I can show you 2 examples. This is an anteroposterior view of the pelvis in an adult female. This is the illustration from the textbook. This is a radiograph from the UK hospital. This is an illustration of the phantom with a bounding box for the irradiated field. This one shows internal organs, and this one shows just bones. And we use these so that if we felt that, for example, the field was extended too far inferiorly, we would say, raise the inferior margin by 3 centimeters, or move the lateral margin outward by 1.5 centimeters. And the modeler would do that, and we'd get it back and look at it and decide if that was okay or not. And if not, then we would give additional instructions. Here's another example of the view from the illustration from the textbook, the radiograph from the UK hospital, a phantom with all of the organs, and a phantom with just the bones. All of these final determinations of the projections are shown in Annex B for each of the examinations that was modeled. And that is it. And I thank you, and let me stop sharing and turn it back over to Nina.
Well, I would like now to introduce you Yeon-Soo Yom, who is going to continue with the calculation methods. So,
Okay. Okay. I'm not sure my video doesn't turn on, I think. I cannot turn on. But yeah.
See it.
So can you see my screen?
we see your
Now,
slides, yes.
okay. Okay, hello. Thank you for introduction, Nina. I'm Yeon-Soo from the Yonsei University, South Korea. I'm in this presentation. I'd like to introduce how we calculated those coefficients by Monte Carlo simulation using the phantom. So here are the contents. The first, I would like to introduce first the reference phantom, which is about chapter 2. And then I will explain how we calculated those coefficients for monoenergetic photons, which is covered chapter 4 in our report. And then lastly, I will explain about those coefficients for the example X-ray spectra, which is also covered chapter 5 in our report. Okay, so let's start with the reference phantoms. So this slide shows the ICRP reference phantom series used for those coefficient calculation. So as you can see that the adult male and female phantoms are released through the ICRP publication 110 in 2009. Then after about 10 years later, in 2020, the pediatric male and female phantoms are released in ICRP publication 143. And these pediatric phantoms cover the 5 different ages, 15, 10, 5, 1, and newborn years old, 0 years old. So so this is 10 set of the phantoms. So this is adult and pediatric phantoms used in, this is the Boxer model actually. The Boxer model, the constructed from the CT images of the real human bodies, and also very carefully match to the ICRP reference anatomical data provided in ICRP publication 89. So these reference Boxer phantoms significantly improve the anatomy and therefore dosimetry, especially when compared with the previously used the mathematical phantoms. So mathematical phantoms previously used the ICRP, those coefficient calculation before the ICRP 103 general recommendations. So this is an example of the mathematical phantoms developed by Oak Ridge National Lab. As you can see, where the shape of the body and organs are tissues actually presented by using the mathematical formula, such as cylinder and ellipsoid. So you can see the Boxer phantoms can significantly improve in anatomy and dosimetry. So this table shows basic numerical value of the reference phantoms, such as Boxer array and then Boxer size, and standing height and body mass, particularly height and weight for each phantom, each age and gender are matched to the ICRP reference value. And importantly, the reference phantoms include all organs and tissues considered at risk of stochastic and or deterministic effect in the current ICRP recommendations. In other words, these phantoms include all the organs and tissues required for effective dose calculation and also the range dose calculation. And this mass of these all organs tissues are also again matched to the ICRP reference data. It should be noted that only skeletal tissues, the red bone marrow and the bone surface are not explicitly modeled, but implicitly considered in the reference phantom. I know this skeletal issue is a little bit complicated to understand, but it is technically important to understand how skeletal tissues are considered in the reference phantom. So I will explain it a little bit more. So as you can see in this picture, the red bone marrow and the bone surface are distributed within the skeleton as highly complex and microscopic structure. So it is easy to imagine that such complex and microscopic skeletal tissues are hardly identified from the original CT images used for phantom construction. So it was technically impossible to exactly define this skeletal tissue in the phantom. So despite such difficulty, at least the reference phantom defined the macroscopic skeletal region, the cortical bone, spongy bone, and medullary cavity. So we consider this microscopic skeletal region as a homogeneous mixture of the various microscopic skeletal tissues, such as the bone marrow and bone surface. So given this situation of the skeletal system of the reference phantom, we need to consider a special approach for the skeletal dosimetry calculation using the reference phantom. So which will be explained more later. And as a result, the observed dose to all the necessary organs and tissues can be calculated using the reference phantom. So next, I will explain how we calculated those coefficients for monoenergetic photons, again, which is covered in chapter 4 of the report. In this report, we provide 3 types of monoenergetic dose coefficients. The first one is air karma for fluence at 1 meter from the source. So this was calculated ideally by emitting the monoenergy photons in the free and air medium in Monte Carlo simulation. And then the second one is organ observed dose for fluence at 1 meter, at 1 meter from the source. These organ dose coefficients were calculated by irradiating the defined beam field as explained by Don to the phantom with monoenergetic photons in Monte Carlo simulation. So this picture shows an example of the exposure of the chest PA for adult male. So once we have the organ dose coefficient, we can easily calculate this the male or female contribution to effective dose coefficient. This can be simply calculated with organ dose and radiation and tissue weighting factors. So before those coefficient calculation, we identified a small issue on the different posture between phantom and patient for some imaging examination. So for example, when we consider chest lateral examination as shown in this picture, the patient normally raise their arms up in order to avoid unnecessary beam attenuation by arms. However, this arms up posture is different from the ICRP reference phantoms, which are fixed with arms down posture. So to address these issues, we simply use the reference phantom without arms in Monte Carlo's calculation for a part of examinations. So please see table 4.1 in our report to understand which examinations were simulated using the phantom with arms or without arms. And this slide summarizes several key information on Monte Carlo dose calculation. So adult dose coefficients were calculated using the easiest NRC and XCOM database was used for cross-section data, and photon energy up to 150 kb with the 1 kb step were considered, and 10 to the 7 primary photons were used for each calculation case. both photon and secondary electrons were simulated, which means that we did not consider chroma approximation. And the pediatric dose coefficients were independently calculated using Gent4 code, and the cross-section data, the Livermore data used. And the maximum photon energy was practically considered different with age. So newborn 80 kb, 1 year 90 kb, and 15-year 120 kb. Again, the photon and the secondary electrons were transported here as well. So as I mentioned before, it is necessary to use a special approach for the skeletal dosimetry. So this is the use of the photon influence to skeletal dose response functions. Simply we call the DRF. So here in the equation. So these DRF values were derived based on the micron CT skeletal images. So as a result, during the Monte Carlo dose simulation, we actually calculated the photon influence for each bone site, which was then multiplied by the DRF value to finally get the skeletal dose. I know this skeletal dosimetry is somewhat complex and difficult to understand. So the key information here. So please see ICRP publication 116, where the detailed information on the DRF-based skeletal dosimetry is well described. And also please see the Annex C in this report. So you can see how the skeletal dosimetry is practically implemented in different Monte Carlo code. And also these DRF values actually not tabulated in this report, but already tabulated publication 145 still in Presto. So these are key information for the skeletal dosimetry you can check. This graph shows an example of the organ dose coefficient for scoliosis right lateral projection and male pediatric phantoms. So as you can see, there are some variation depending on the ages, even though the amount of the variation and trend are different with different the organs. So this is an example. So anyway, all the values of the monoenergetic dose coefficient calculated will be provided in the electric supplement. And also we also conducted quality assurance for checking the monoenergetic dose coefficient. So to do this, those coefficients were compared with the additionally calculated dose coefficient for some selected examination as a spot check calculation. So these spot check calculations were conducted by independent group who did not conduct primary calculations. So for other dose coefficient, one group was involved in spot check calculation using Gent4 code. For pediatric dose coefficient, two groups were involved in the spot check calculation using EGS NRC for one and using Gent4 for the other. So here are also some examples of the quality assurance result. The left is the adult female pelvic AP at 100 kV, and right is the newborn male chest AP at 50 kV. So you can see there are excellent agreements between primary and spot check calculation, the most of the organs and tissues. Of course, you can see some disagreement organ you can see, but these organs are completely out of the beam field. For example, here the range is here is completely different, so that's why the statistical error is quite large. So we can see some variation. So next, I will explain how we calculate those coefficients for example X-ray spectra, which is covered in chapter 5 of the report. So in this report, we provided 10 types of those coefficients for the X-ray spectra, including the organ and effective dose coefficient in this report. So in addition to the fluence at 1 meter from the source, as I said in monoenergetic dose coefficient, here we also consider two measurable quantities, the air karma and karma area product. So for other examinations, we selected X-ray spectra depending on 4 different tube potentials, and then combined with the 3 different aluminum filter thickness. So these X-ray spectra apply for all other examinations. And then this spectrum obtained from the spectral program, which is a very well-known program to generate the X-ray spectra in many different parameters. So this is an example, the obtained X-ray spectra from the spectral program, about 4 tube potential with 3.5 millimeter thick aluminum filter. And for pediatric examination, please see the table 5.1. You can see here you can see the selected X-ray spectra depending on the age and the examination. So these spectra again obtained from the spectral program. Spectral dose coefficients can be actually easily calculated by convolution of the previously calculated the monoenergetic dose coefficient with the relative number of photons for each energy, which can be obtained from X-ray spectra. So the calculation is very straightforward. So this table shows some example of the organ dose coefficient for the chest AP 5-year male, where the 4 different filters and at all tube potential is 70 kV. So once again, and this is the per those coefficient per fluence. Here is per air karma and carp. So once again, those coefficient value will be provided in electric supplement. We also performed quality assurance of the spectral dose coefficient derived from the convolution with the monoenergetic dose coefficient. So for this, we compare the value, additionally calculated value from direct Monte Carlo simulation using the X-ray spectra. So as you can see, there are excellent agreement for most of the organ and tissue. Only few organs, such as eye range, again show some disagreement because these organs are completely outside of the beam field and have large statistical uncertainty. So this is the short summary of my presentation I explained so far. So please see the reference phantom in chapter 2 and the monoenergy dose coefficient in chapter 4 and X-ray spectra dose coefficient in chapter 5. Okay, so thank you so much for your attention. Okay, I will start my sharing slide.
Yes, David, thank you. Please continue with the examples and the electronic supplements.
Thanks, Nina. I'll just turn my video on. Hello, everybody. I'm going to talk today about how to use the Bremsstrahlung spectra data to estimate organ effective doses and give an example. I'm then going to move on to talk about how convolution is used with the user-defined spectrum to estimate organ effective doses, and I'll describe the method and give an example. I'll discuss some limitations and uncertainties in the overall calculations that are detailed in the report. I'll then give you some information about the data sets that are available and will be available, and the viewers that you will be able to use to interrogate them. And finally, I'll summarize the report. So first of all, how to use the Bremsstrahlung spectrum data to estimate organ effective doses. As you've seen in Yonsu's presentation, for adults, we have coefficients for each projection at 60, 80, 100, and 120 kV. So that's altogether 384 sets of coefficients for each normalizing quantity, fluence, Kerma, and cap. And for pediatrics, we have a total of 496 coefficients, both of which are detailed in the tables in the report. So, to estimate the doses using the spectrum data in the report, you'll need, first of all, a measurement of the Kerma free in air on the central axis of the beam at 1 meter from the tube focus, or the cap for a specific radiographic view. You'll need to know the tube potential in kV used to the exposure, and you'll need to know something about the tube filtration or an estimate of it. We suggest 3 millimeters of aluminium if you don't know. So here's the specific example. The examination is an abdomen AP. We want to know what the absorbed dose to the colon is using the adult male phantom. The tube potential is 80 kV. The filtration is 3.5 millimeters of aluminium, and the Kerma area product is 2.5 gray centimeters squared. So the first thing you need to do is to open the file in the data sets called abdomen AP spectral, shown here. Okay, and next, open the AM sheet. I appreciate you probably can't see this very well, but the AM sheet shows us the organ dose per fluence in the reference plane, the organ dose per air Kerma in the reference plane, and the organ dose per air Kerma product. And down here we have beam qualities, kV and filter, and across here we have the organs. So I'll just magnify it up a little bit to show you the area we're interested in, which is we're interested in the organ absorbed dose per Kerma area product. We're interested in 80 kV, 3.5 millimeters of aluminium, and we're looking at the colon. And this shows us quite simply that the dose coefficient here is 0.426 milligray per gray centimeter squared. So to calculate the colon absorbed dose, we multiply these two together, cap and the dose coefficient, and we get an absorbed dose of 1.07 milligray. So that's pretty straightforward. And now we're going to talk about using convolution with a user-defined spectrum in order to estimate organ effective doses. Well, why might you want to do this? You might want to fine-tune results. You may not have a spectrum that is commensurate with ours. You may have harder beam quality. You may have different filter configuration. Alternatively, you might be doing an optimization project, or you might be looking at something like novel filtration. So here I'm showing something that doses cannot be estimated using the data in the Bremsstrahlung spectrum. This is the X-ray fluence spectrum from a hard beam with 3.5 millimeters of aluminium filtration plus 0.7 millimeters of copper. And the report doesn't produce or present bespoke coefficients for hard beam qualities like this, but you can do it using convolution. So here is an example, and I'm going to use the same as the one I've already presented using the spectrum. So it's abdomen AP. What is the absorbed dose to the colon for an adult male at 80 kV, 3.5 millimeters of aluminium, and a cap of 2.5 gray centimeters squared? So the first thing you need to have is the X-ray fluence spectrum for your beam. So here it is, 3.5 millimeters of aluminium, 13-degree target angle, 80 kV. To generate this, I've used the IPEM Report 78 spectrum generator. So you don't need to use SpecCalc. You can actually use anything that you have available. To carry out the calculation, it's necessary, oh, I'm very sorry. To carry out the calculation, it's necessary to fold the fluence spectrum with the dose coefficient per fluence in the reference plane. To get this data, you need to open another spreadsheet. This is the one called Abdomen AP Mono. This gives you the air kerma per fluence at each energy, and in our case also the colon, so the air kerma per fluence and the colon dose per fluence at 1 meter. To fold the two together, you have to use this equation, which at first step doesn't look very easy, but actually it's quite simple. And what we do is we give you a flow diagram that takes you through this in a step-by-step manner to enable you to perform the calculation in a spreadsheet or using your own program. This is a flow diagram here. I'm not going to go through it for obviously reasons of time, but you can find it in chapter 6 of the report. And also in chapter 6, we give you a worked example showing you how to use the flow diagram with data that you've got from the fluence spectrum and from the data set. And the important thing to notice here is that once again, for the same equation, we get that the colon dose coefficient is 0.426 milligray per gray centimeter squared, which is exactly the same as in the last example. So, in other words, both methods yield the same result, 1.07 milligray. And it's perhaps interesting to notice that this result and all other results are of a similar magnitude to those found in previous publications. I've here given an example from an RPB publication 262, which had 0.91 milligrays, the colon absorbed dose, for the same examination. The report provides other examples of the use of convolution. Here is one: an investigation of the variation of the colon and effective dose coefficients in abdominal examinations resulting from different beam qualities using the 5-year-old phantom. And here we have different beam qualities, 70 kV, 0.2 millimeters of copper, 65 kV, 0.1 millimeters of copper in addition to 3 millimeters of aluminium. These are not in the data sets provided, but the dose coefficients can easily be generated, as can the effective dose coefficients as well. So moving on, and as you might expect, the reporting includes some consideration of the uncertainties and limitations involved in the work. Topics include, as listed here, the influence of the voxel phantom itself, the fact that the reference field position might not be replicated in real life, the uncertainties in the interaction cross-sections used in the Monte Carlo calculations, the fact that, as Jens mentioned, organs distant from the primary beam will have poorer statistics than organs in the primary beam, source geometry, uncertainties in the dose estimates themselves. For example, measurements of normalization quantity. There's a very big uncertainty in measurement of cap. Use of the mediums, size, some of the underlying assumptions that we make in the report, things like the influence of heel effect and so on. So all of these are discussed in chapter 7 of the chapter, and we'd be interested indeed in your views of this. I haven't got time really to cover them because there are quite a few to talk about. So the consultation document that we're talking about today comes with 2 examples of data files, rather, that you enable the readers to study the worked examples. However, the final report will contain a full electronic supplement containing all of the data. The supplement will be organized into 26 main folders, one for each of the projections considered. The first will tabulate, each folder will have 2 subfolders as shown here, and the first will tabulate the dose coefficients in 1 kV bins as dose per fluence at 1 meter from the source, and the second will provide dose coefficients for the selected Bremsstrahlung spectra, which, as you've already heard, are reported as organ absorbed and effective dose per cap and per echo in free and air at 1 meter from the source. The data will be provided in Microsoft Excel spreadsheets, and also as ASCII data files. And you've already seen this slide from Nina. The data files provide organ-absorbed coefficients for both male and female phantoms at each reference age. They'll also provide for each examination and phantom a coefficient for either the male contribution to the effective dose or the female contribution to the effective dose, and of course, in most cases, where appropriate anyway, effective dose coefficients, which is the sum of these divided by 2. And there will also be viewers bundled with the report itself. This is an example of the monoenergetic data viewer. Sorry, it's not. This is, sorry, I'll start again. Data viewers will be made available either bundled with the report or externally. The external dose viewer will be an extension of the current ICRP viewer that you can get from the App Store or on Google Play. And the data from the selected spectrum will be available as part of this viewer in due course. So here's an example of the ICRP viewer available from the App Store, showing how radiographic exposure tab works. In this example, the examination is a pelvis AP performed on a 5-year-old female, with 3 millimeters of total filtration. The cap is 0.2 gray centimeters squared, which is close. I chose this because it's close to the DRL for that examination. And you can see that the sex averaged radiation dose will be effective dose. Sex average effective dose is reported as 0.118 millisievert. The target organ doses will also be shown, and they appear below. You can see that in this case, the colon dose is 0.302 millisievert. So this is a handy tool to enable you to view the exposures or the doses from the spectra that are provided in the report. However, there will also be viewers that are bundled with the viewer themselves in the report with the data sets themselves. And this is an example of the monoenergetic data viewer, which is a macro-enabled Excel spreadsheet. It enables the user to plot and extract dose coefficients for up to 6 conditions. I've chosen 6 here, or for the pelvis APs, using different sex-specific, tabulating this different sex-specific ED for a 5-year-old male-female, 1-year-old male-female, and the neonate, showing you how they vary, the monoenergetic coefficients vary with energy, and also allowing you to extract the data for each of these 6 conditions extremely easily. There will also be a similar viewer for the Brem-Strahling spectrum-specific dose data. So 3 viewers altogether, 2 bundled with the report, and 1 available from the App Store. So finally, just to summarize what you've been told already, before we go on to the Q&A, the publication describes the ICRP approach to developing a standardized method for the determination of organ-absorbed and effective dose coefficients for radiographic imaging for a range of examinations commonly performed on adults and children. The target audience is aimed at all those who have an interest in patient dosimetry and optimization, including national and international authorities, medical physicists, radiographers, researchers, radiologists, and other radiological practitioners. The organ-absorbed doses and effective dose coefficients provided are estimated for a reference person at each age, so they are reference dose coefficients. They're specific to the exposure coefficients specified. They've been calculated using the ICRP methodology. And it's important to remember that the care needs to be used when using these dose coefficients, because it's the dose which the reference person would experience if irradiated with the same exposure conditions as an individual patient dose. And that's an important caveat to the whole endeavor. And with that, I'll stop my presentation and hand you back over to Nina. Thank you.
Thank you very much, David, and all the other speakers for the presentations. So we are well in time, and we have so that we have time for addressing your questions. So the way that I will try to do it is going through the text and pick up the questions and address them to the different speakers. Before I do that, I would like to introduce you Dr. Kimberly Applegate. Can you all please switch on your videos? So Dr. Kimberly Applegate is a pediatric radiologist, and she's the chair of the ICRP Committee 3, which is dealing with radiological protection in medicine. And she's also one of the 2 radiologists who is a member of our task group.
I can't turn on my video, but I can turn on my my voice.
Okay.
Now I can start it. I've got it. Thank you.
Okay, here you are. Thank you. Okay, so let me. I will pick up one for myself first. The skeletal response functions, fluence to skeletal dose conversion, is available for adult in ICRP publication as a separate table in ICRP publication 116. But for pediatric phantoms, it's still not available as a separate table. Will be available in this publication. Note that dose response functions will not be available in this publication because they will be part of the electronic supplement of publication 155, which is on the queue, so it's going to come out, any moment. Publication 155 is on specific absorbed fractions for reference pediatric individuals, and there you will find the DRF's values. But what we have in this report, as Hyun-Soo has described, is that we give practical instructions for using those response functions in your Monte Carlo codes. Okay. So David, there's one for you. Please, is there any simple formula that employ the use of KV and MAS for diagnostic radiographer to calculate the ICRP's recommended absorbed dose for all conventional X-ray examinations?
I'd also like to comment on that after David.
Sure, thank you. David, would you like to?
I'm trying to understand. Can you hear me? I'm trying to read the question. Is there any simple formula that employs these?
Well, you're
MAS
doing that.
If you need to know at least the air Kermer per MAS to get to use the Bremsstrahlung spectra. I think is that what the question's asking?
No, it's about protocols. I mean, it's about it's for radiographers to understand protocols, and this is very much about practicality. If you're in the room, you need ideally you measure the thickness of the patient on the table. Say, okay, if they're 10 centimeters, thick, this is the adjustment to the KVMAS to get an ideal abdominal or chest radiograph. So you have protocols embedded in the machine to take your radiographs, your protocols, your common protocols, and you develop that. And there are many of these are available either on the AAPM website, on the Image Gently website for children, on the Image Wisely website. So these may be very helpful as references. So that's something you can do. So this is a very practical question, that is being asked. So anyway,
Is there any simple formula to employ the use of KV and MAS to so I'm assuming it means if you've used, for example, an AEC, you have your KV and your MAS is displayed, and the question is asking how you can use the displayed KV and MAS to estimate the absorbed dose. You can only do that, I think, if you know the air Kermer per per MAS at the KV. If you haven't got that information, I don't believe that you can do it. You need, or the cap. I would expect that most of the time X-ray equipment displays Kermer area product that can then be used with the dose viewer or the spectra to calculate the recommended absorbed dose.
They may or may not do that. They may indicate only an exposure index, which is not a consistent metric. It varies from manufacturer to manufacturer.
Right.
And the
Okay,
necessary KV and MAS are determined primarily by the patient's body thickness
Yes.
and the necessary image quality, but also by the equipment itself. Various image receptors may vary in their ability to convert photons to images. So there isn't one answer for every situation.
No, there's not. I agree. I agree. I think in the UK, all X-ray equipment displays the Kermer area product. I'm not sure about the US or other parts of the world. But if you have a measurement, in that case, you would need to have a measurement of air Kermer per MAS at the KV, which your medical physicist will have done and should have tabulated for you. And you could easily get that tabulated. If they haven't done it, you could ask a medical physicist to tabulate or to give you an indication of what at any KV, what the air Kermer per MAS
Just a
is.
comment, there may not be a medical physicist for the facility, just, you know.
Yeah, indeed. Indeed.
Yeah.
Okay, so I'm staying in the same framework more or less for the next question. That is again for David, Don, or Kimberly. The Excel example is very intriguing. I have one query regarding the simulation. When we're doing abdominal scan, the radiation field size covers the abdominal region. It may happen that the extreme parts of the body, feet or other portion, will receive very less radiation and hence will result very less absorbed dose. You say it, very less absorbed dose. And hence larger uncertainties of the Monte Carlo.
I think those are the questions for you and Yonsu, actually.
Yes, yes. Well, hold on a minute.
Sorry.
First of all, the feet are not in
Yeah, I just
the...
typed the answer of that question. So
What
please
did you
look at.
say?
Okay.
Can you? Yeah, maybe.
Maybe you read the answer out, Yonsu, please.
Okay.
Yes.
So the absorbed dose to the organs and tissues outside beam field are calculated with large uncertainty as well, but the value is very small, as you know, because it's very far from the field. So the effective dose are determined by the organ dose inside the beam field, actually. So the contribution of the organ dose outside the beam field to the effective dose is indeed very, very small. So we can ignore.
Yeah.
So that's the
It's a
point.
couple of orders of magnitude below. Okay, we will try to answer the questions live. Well, when will the final report be published? Well, the final
That's a
report
big question.
Yes, well, the final report, we are now in public consultation until the 16th of August. Then we will consider all the suggestions for improvements and clarifications, and we will produce a better document. And then it will go to the queue with the ICRP publisher. So, I mean, I don't know. I hope that it's going to be published this year. That will not be completely depending on our hands, but depending on, as I said, on the publisher. And then, well, they disappear, the questions. I'm not ready yet. In the same question was, what about the CT and the rest parts? So, indeed, the dose coefficients for the CT are the part 2, which is going to come next and soon.
But the caveat is that a cone beam CT is not being looked at. We do have a publication on cone beam CT, but it's not for dose coefficients, right? We do have some cone beam CT in Task Group 116
Okay.
that has not been published yet. We have information coming out with that.
Okay. Well, I
And
was,
it is for in radiotherapy, not
Okay.
in dental, but in radiotherapy, pre-treatment and during treatment evaluations.
okay. Yeah, I was referring to the dose coefficients, to the work of this group. So CT is going to be the next, and I'm hopeful that the document will go to public consultation by the end of the year, and then start the process. Okay. Next, thank you for the presentation. In the second presentation, Don, I noticed that the data set was focused on US or UK. Is it that there is no reference data from continents like Africa or Asia? Also, are we to assume that those coefficients, like other coefficients that have been developed previously, are directly applicable to people in this?
I can take that. The data that we used was for the US, the UK, Europe, and level 1 countries, but that was only to determine the frequency of examinations to help us choose which ones to model. And given the consistency of all of the data that we looked at, there's no reason for us to consider that it is any different in countries elsewhere in Asia or in Africa. And is it applicable to other populations? Well, remember that the data that we're providing you are based on radiating phantoms, not individual people. So these are the doses to ICRP phantoms, and they are as applicable to anyone in any country around the world as to anyone in any other country around the world. They are not to individual patients.
Yes, if I could just come in as well and just remind you of what Nina said, and I also said that we need to be aware that these are doses to reference phantoms, which just to emphasize what you're saying, Don.
Okay. Now there are a couple of questions on the ICRP dose viewer that Lisa Marie wrote that she cannot download the viewer. Well, that surprised me. What we mean, download the viewer from the App Store of the Google Store. So if you, and it's free, so not in the browser.
Can I just come in there? I've just tried to download it from the Apple App Store. And whilst I managed to download it last week, this week it tells me it's not available in my country. But it is available on the Google Store currently. I'd also like to just emphasize that the diagnostic radiology coefficients are not yet in the dose viewer because the publication hasn't been finally signed off. So they will not be available until it's published. But maybe a question to Charlotte about the availability of the ICRP dose viewer, if we have an answer on that.
Someone is looking into it. It also is not available in certain countries or certain app stores, but is being looked into.
Yeah, sorry, we were made aware of that last week, and ICRP, like the secretary, doesn't necessarily monitor that, but Martin Anderson is looking into the issues with that, and hopefully that is sorted soon from the App Store perspective.
Thank you.
Okay, now a couple of questions for you, Yunsu. Please answer the questions live. Then, so it was a question about the doses to the fetus, and if we have any plans.
Okay, so yeah, I just typed the answer. So I think we in our task group we have a plan. We have a future plan to produce the factor dose coefficient as well in the future, but not in this publication. But we have a plan. Yeah.
Yeah, well, we've started. We have just kicked off this part of the work.
Mm-hmm.
So individual patient doses do sometimes need calculating. would ICRP do any work on how to adjust the reference calculations to different size patients? I've heard mention of ICRP perhaps defining patient effective dose, but haven't heard much about this recently. David, would you like to take this?
So can you show where is that question so I can read it, please?
Andrew Schaffer.
Yeah, Andre Shepard.
Otherwise, I'll take it.
Individual patients do sometimes need calculated ICRP do only work how to reference calculations to different size patients. That's a plan for the future, isn't it, Nina? We're going to use the new reference phantoms, the mesh phantoms, to to adjust the reference calculations for different size patients. So the plan is 95%, the 95th percentile and the 5th percentile. That's one of our future future aims. I'm not quite sure what the mention of ICRP defining patient effective doses. There is work going on with regard to the reformulation of the recommendations looking at effective dose, but that's very much work in progress or not even started yet. Did you want to add something, Nina?
Yes, well, I just want to extend what you've been saying. So by considering different size of patients, then we will study the variability. But of course, if you are talking about effective dose, there's a lot more into it, because the most important factor on the effective dose, or one of the two important factors, are the weighting factors, and different weighting factors from different ages and different sex and different population groups. So this is a different story, which is looked now by a new task group, task group 128, I think. But this is still very early to say anything about it. It's something, for the future. Mm-hmm. Depends mainly on how one would judge the epidemiological data and the uncertainties in this in risk factors that are, as I said, population specific. Mm-hmm. So our work at the moment is for reference phantoms, reference individuals that give approximate estimation of the patient dose. And this approximate estimation can be used, as I said, for optimization, for seeing which technique is giving more or less dose, and also for estimating population doses. But it has to be used with big caution when it is translated automatically to patient dose. So this is not correct. It's an approximate approximation to a patient dose. So,
Nina, there are a couple of questions that are similar about what do you do with obese patients? And related to it, there's an anonymous question about how do you decide what a typical patient is? So, we have the reference phantoms, but we also have in our mandate to look for potentially, after we've finished our main program of work, to look at the 5th and 95th percentile size patients. And maybe you want to address those.
Yes, thank you. Yes, exactly. I know there were a couple of questions for you and Sue.
Okay. So many questions.
Let me see.
Could I maybe address the same one that Kimberly just did about the level of uncertainty in patient anatomy and patient images? You're absolutely correct that there is a good deal of variation. If you remember from my presentation, the two sample chest x-rays were of very different individuals. One was tall and relatively thin. The other one was wider through the chest. The goal was to represent on the phantom the anatomy that we tried to see on a radiograph. So we weren't accounting for uncertainty, we were attempting to mimic what is seen with that specific ICRP phantom. And really that's all, because all we were doing was deciding what the phantom would be exposed to.
Okay, thank you, Don. So there's a question from Safa. Well, just to recommend a free download software to calculate overdoses for CT. So for CT, we're going to provide this software when we're going to be ready with our CT work. As I said, it's not going to be long. And radiography. So for radiography, we will have this the two viewers that David has introduced.
Mhm.
Would your report have some reference to fluoroscopy modality and images? Our report not. These are two separate work streams that we will address in other publications. The work is already in good progress. Yansu, let's take this one. Other organs like the brain would also be outside the radiation field. In this case, there was not as a discrepancy between the method as with the lens of the eye. I'm not sure that I understand that.
So which I cannot see that question. Is it
3:12 p.m. I mean, in my time, Jamie Peffier. Well, I'm not sure I understand it, but of course, if the radiation field is in the head, then the lens of the eye would have, from the Monte Carlo calculations, enough counts so that the Monte Carlo uncertainty will not be large. But of course, if the field is somewhere else, it's in the abdomen, for example, and you have the lens of the eyes, which is very small volume anyway, then the discrepancy, the uncertainty is larger. But on the other hand, as Yansu said, the dose is very, very low.
Yeah, I just found the question. Okay. Yeah, that's correct. Then
David, as a medical physicist and RPO, usually radiographers asked about whether we use ADR, automated dose reduction, using exposure patients.
maybe
I think the question is about what in the US we call automatic exposure control or automated exposure control,
I wondered if it was that, yeah.
where the technique is determined by the equipment when the image receptor or the sensor receives enough photons.
Mhm.
Can the convolution method be applied to any novel filter, so long as you have the spectrum distribution with matching KV and target in the report?
Yep.
Could you please repeat what spectrum generator you used rather than spec out?
Okay, yeah. So the answer is you can use the convolution method to any novel filter as long as you have a spectrum distribution. And the KV, as long as it's less than 150 kV for adults, and any whatever the maximum KV for the examination for the pediatric examination is. So you could, for example, I did have an example of a novel filter, but I took it out because it was too difficult to include. But you could have something that sharpens off the K, sharpens off the edge near the K edge, like an erbium filter or something, and you could investigate the use of that. as long as you've got a suitable spectrum generator. The one I used was IPM report 78. That's just because it was handy for me, and it comes with a lot of filters, and you can add your own filters as long as you know the Mu-Rho coefficients for them that you can get from Hubble's tabulated data. So yes, is the answer to that question. There's a question that says the dose viewer only includes doses due to intake of radionuclides. Well, I think we've answered that. The radiography is not clear yet. Yeah.
Yes. Yeah. Of course, we do not release the electronic supplements until the publication of the report. There was another question that I answered in writing. How can you get the electronic supplement? The electronic supplement can be downloaded when the report is out of publication, but not before.
Mm-hmm.
Can I consider that the effective dose calculated by convolution is a personalized dose?
No.
No, I mean it is a dose for this spectrum that you are convoluting.
To the reference phantom.
For the reference phantom.
Yeah.
And there was another question, which I mean, it's fair enough, that the typical patient is varying with time. 60 years ago, an average UK male was 65 kilograms in weight, and now he's 80 kilos. Well, you of course have a point on that.
I would certainly agree with that, but again, this is a question of, is the ICRP Phantom sufficiently realistic for real life? And I don't think it is personally, because it doesn't represent anything other than an idealized individual. It does not represent the entire population, nor can it. And if you think of the upcoming Olympics and you look at a typical female gymnast who is quite short and compare it to a typical basketball player who is typically 2 meters or taller, there's no way that the Phantom represents either one of them adequately.
Yes. But the weight or the height is also quite variable in different parts of the world. So this is something a challenge. So what else? I think
there was a question about ambient dose, ambient temperature and pressure, and that is really just about the uncertainty in the calculation. And you would have to take, if you don't make an ambient temperature and pressure correction, then that's just going to increase the uncertainty in your measurement of dose when you calibrate the cap meter. And that's discussed in chapter 7 of the report. That's a question from 1416, my time.
There's another question at the end. Is there an influence of scattered radiation in the estimation of doses at the level of an organ? Yes, absolutely. Scatter affects the dose to every organ outside the area that was irradiated, as we heard earlier with a discussion of the lens of the eye and the brain. So it certainly operates to increase doses within the field as well.
Mm-hmm. Mm-hmm.
The ICRP dose viewer provide alarming thresholds that are considered alarming when the calculations are done. No, the ICRP dose viewer is just giving the doses or the dose coefficients, depending on what viewer you're referring to.
I think along those lines, it's worth pointing out that effective dose is not really intended to be used as a method for optimizing exposures. The ICRP has implemented diagnostic reference levels for that purpose. See publication 135.
Yeah. And that The usual quantities for DRLs are easily measurable output metrics from X-ray equipment, so CTDI, DLP, Common product, etc., etc.
Yeah.
The last question, the difference in bone composition for different ages. Yeah, I think different bone composition for different ages we considered.
Yes, yes.
And but races,
No,
yeah,
races,
no, but ages we consider the different bone
Yes.
composition. Yeah.
Yes.
Will be the webinar will be the registration of the webinar will be available.
The webinar is recorded, so in the event website you can find in a couple of weeks the recording and also the slides that we've presented and a short protocol of the questions that we have answered and those that we did not answer. We will include them also in this protocol.
There's a question, 1426. Balancing radiation dose and image quality is important. The task group works the quantification and evaluation of workflow, but any plans to quantitatively assess image quality? That's discussed in the publications that are coming out from TG108. So publication 154, which I'm not sure if it's published or not, Kimberly may know, or Charlotte may know, addresses that, as does part 2 of that report, which look into, in some depth, the evaluation of image quality and how to take that into account in the very important topic of balancing radiation dose with image quality.
Right. We don't know when
Sorry, Kimberly?
it's coming out. It's ready.
It's on the horizon. It's
It's
very,
ready.
very close.
Yeah. Thanks.
Charlotte, did you want to add something in the registration, the question about the registration?
You guys covered it. We'll have a video out of this within a week or two, as well as you said, any unanswered Q&A questions will be available on the event webpage.
Okay, I think we've gone through all the questions. Oh, there is one maybe we haven't, because we mostly don't use air camera index when exposing. We only have milliamperes at TV. Yes, we refer to the body density or habitus. I'm not sure. I think we discussed that, and that was a reaction to our answer.
There's a question at 1406 about CBCT from Tim Wood. There are currently no plans that I'm aware of to produce dose coefficients for CBCT. The doses that have been produced for the computed tomography project are specific to conventional CT, and the dosimetry for CBCT is very different. Even though CTDI may or may not be used, it's not the same CTDI. So we're not currently any plans to do that. And we can't extend the work that we've got because it's based on the characteristics of what you might call conventional computed tomography scanners.
So if there is no other question, I think
2:30.
we're done. And then I would like then to close today's webinar by thanking the speakers, by thanking Charlotte White and Kelsey Cloutier for supporting us during this webinar, and of course by thanking the attendees that they joined us today. And I hope to see you soon again to a future webinar of our task group dealing with the other parts of our work. So thank you very much and have a nice rest of the day.
Okay,
Thank you
thank
very
you.
much.
Bye.
Bye-bye.